At the end of the last video, I came to this result, and I think I kind of rushed through defining it. So I want to go ahead and state it again because it is pretty important. And it's also pretty important that you understand what this term means, what this term polynomial means if you've never heard it before. So I'm actually just going to go over here, get myself some more space. And let's see how far up I can go. I can go about there. So first, let's define what a polynomial is. Polynomial. So a polynomial is basically just going to be some function. Let's call it, we've been calling everything f of x. Let's call it g of x. It's going to be some function g of x that's just going to be collections of powers of x multiplied by some constant coefficient. So let me write this down. I'm going to call this a 0 plus, and let me put this in, a 1 times x, and you can imagine that's x to the first power, which is the same thing as just multiplying by x, plus a2. And these a terms, these are just some number. They're some constant. It's like I was putting in, 2 times x1 and 2 times x to the first power. And then on a2, we've got x squared. It's like saying, if I was saying we had 4x squared, and then plus a3 times x cubed. And if I kept going, if I kept adding terms onto this up until we got to the term just a sub n times x raised to the nth power. And I just kept adding, as many terms as I had in my polynomial. If I had, 100 terms, if I had 5 terms, however many terms, this would be the format of that polynomial. I would just have powers of x multiplied by some coefficient, by some coefficients that we're calling all of these a terms here. So, an example of a polynomial could just be, a linear function. If we said, let me actually say h of x is equal to x plus 1. Or else let me actually write that this way. 1 plus x, and just reverse that order. So in this example, 1 right here, that's this a0 term. That's like the first constant that's in our polynomial. And then we've got something times x to the first power. And in this example, we've got a1 is just going to be 1. And so we've got 1 times x to the first power. And then all of these other a terms are just going to be 0. So this is an example of a polynomial. Another example of a polynomial, let's say, I don't know, p of x is equal to, 7x to the fourth minus 12x cubed plus 17. Again, this is an example of a polynomial. We've got coefficients multiplied, or we've got powers of x multiplied by coefficients. One example of something that's not a polynomial, and I guess I should have maybe made it more explicit up here, but if we had the function, let's say q of x, and we said, let's say it was 8x to the fifth, that's a bad 5, 8x to the fifth plus 17x cubed minus 2x to the minus 5 plus 7. This is not a polynomial, and it's not a polynomial because we've raised x to a negative power. So therefore, it's not going to be a polynomial. For for an expression to be a polynomial, we can only have positive whole powers of x. So we can't have, also, let me do this. Like maybe I'll define another function, r of x. Let's say that I'll define this function as, 8x to the fourth plus 12x to the 3/2. This is also not a polynomial because we don't have whole number powers of x. So in order for us to have a in order for us to have a polynomial, we have to have a function where we have just got we've got coefficients that are just multiplying integer powers of x. So counting numbers, x to the first, second, third, fourth, up to whatever nth power of x that you have. We can't have negative exponents like we have in this example, and we can't have fractional exponents like we have in this example. However, and I didn't explicitly say this yet, but so far all of my a terms, all of these coefficients that I've been writing in, those have so far all been whole numbers, but there's no reason I can't have, like, let's say I've got another function. Let's just call it f of x, 8.257 x cubed plus, I don't know, pi x squared minus e times x. This is a polynomial too, even though, none of these numbers that I've got as coefficients. So that's 8.275, that's pi, that's e. Even though none of these coefficients that I have on my x terms are whole numbers, because all of the powers of x that I have in this expression, they're all positive whole powers of x, this is going to check out. This is going to be exactly what we're looking for in a polynomial. So anyway, what we said in the last video, and what I kind of rushed through, is that if we're taking the limit of a function, if I was taking the limit as x approached some value a of some function f of x, and we know that f of x is a polynomial. In other words, f of x fits this format that we have up here. We know that when we take the limit of f of x, that is going to be equal to, this limit is just going to be equal to the same thing as if we just plugged that value in, this value that we were approaching, into our function f of x. And we know that because of the limit rules that we've set up, and also because there's no reason that when you take a polynomial, if you were taking these numbers where you've got coefficients on positive whole powers of x, there's no reason for these functions to not be continuous functions. Any polynomial, if you were going to draw the graph of some polynomial, I'll draw my axes down here, and you are going to draw, let's just say we're drawing this function f of x that we had. If you were going to draw whatever this function looked like, this function f of x, say, it did, I don't know, something like that, you would be able to draw this function f of x without picking your pen up off of the paper. There's no point where, you'd be drawing the function and you'd have to say, oh, but it's not, it's not defined at that point, so we have to put a line, but then it is defined down here. There's no point on the function where you would have to do something like that. If you know that your function is a polynomial, every point on that graph of the polynomial, you could say, is approached to by the previous point and the next point. So therefore, if we're taking the limit of some function f of x, and we know that f of x is a polynomial, then it's really easy to take that limit. We can just plug our whatever value we're approaching into that function. Let's just do a real quick example. Let's say we were looking at the limit as x approaches, let's say, -1 of the function, let's say, x cubed plus 7x squared minus 3x plus, I don't know, plus 5. So let's take a look at this. And so if we were going to take the limit, we could do all of that stuff that we did in the previous couple of videos where we broke this up into, how many terms we have? We've got 4 terms here, and we could do all of that stuff where we would break this up into 4 separate terms and individually take the limit of all those separate terms. But now we've got a really simple rule. If we know that f of x is a polynomial and we're looking for the limit as x approaches some value of that function f of x, we can just plug that value into our function. And so now we can take a look at this function. We've got x cubed plus 7x squared minus 3x plus 5. And this fits the bill for being a polynomial. Therefore, we can just plug in -1 into this function. So therefore, we can say that this is equal to -1 cubed plus 7 times -1 squared minus 3 times -1 plus 5. And then all of this is going to be equal to -1 cubed, that's just -1 times -1 times -1. It's just going to be -1 plus 7 times -1 squared, so that's just going to be plus 7, minus 3 times -1, that's going to be plus 3, and then we have plus 5. So we've got 7 plus 3 is 10, plus 5 is 15, minus 1 is going to be 14. So there we go. We got this answer to our limit problem really, really quickly by using this rule that we figured out, by saying that if we're taking the limit of some function and we know that that function is a polynomial, then it's really easy to take that limit by just plugging the value into the value that we're approaching into that function.